A little bit different look here. The first two we did had two small pieces coming together to make one larger one. Now we have one larger piece breaking down into two smaller pieces, just breaking apart. So I'm going to do the exact same way. K, Cl, and O on the left. K, Cl, and O on the right. Let's just count. On the left, there's no numbers next to K and Cl, so I know I have one of each one. And there's a 3 next to O, so I know I have 3 oxygens. On the right, again, no numbers next to K and Cl, so I have one of each one. And now there are 2 oxygens. Potassium and chlorine are already balanced as is, so I'm just going to have to balance my oxygens. We have to find some number that 3 and 2 both go into. Every time you're doing this, just see, can they go into one of the ones that's already there, or can you maybe multiply them by each other? That's always a way to do it. I'm going to see that 2 can't go into 3, 3 can't go into 2, but we could just multiply them by each other. 6 is still a pretty small number, it's not bad to work with. So I'm going to multiply everything on the left side here, where the oxygen is, by 2 to make this 3 look like a 6. So I'm going to put a 2 right there. That'll give me those 6 oxygens. It'll also change the other 2 elements, though, and give me 2 Ks and 2 Cls. We were trying to get to 6, so now I'm going to multiply this oxygen over here by 3, because 3 times 2 obviously is going to be 6. So I have 6 oxygens. So now we have our oxygens balanced, but our K and Cl are not balanced. Helpful thing right here is that K and Cl are in the same molecule, so whatever you do to K, you're going to do to Cl, and we're trying to change them the exact same way because we want to make these 1 for K and Cl on the right look like these 2 for K and Cl on the left. So I'm just going to multiply everything on the right here with K and Cl by 2. That'll give me 2 Ks, 2 Cls to go along with my 6 oxygens, which perfectly matches the 2 Ks and 2 Cls on the left and these 6 oxygens on the left. So we're nice and balanced. 2, 2, and 3 cannot be reduced. That's my simplest balanced equation. A little bit different look with this. Now we have 2 reactants and 2 products, where before it was either 1 of each and then 2 of the other. Doesn't matter, same step. Ca on the left, Al, and Cl on the left. Ca, Al, and Cl on the right. I look at Ci on the left, there's no number next to it, so that's going to be a 1. Al on the left also has no number, so that's a 1. Cl on the left has a 3, so I write 3. Looking over the right side of the equation, right side of the arrow, I see no number next to Ca, so that's a 1. I see a 2 next to Cl, so I write 2 down here. I see no number next to Al, so that's also a 1. Now I can compare my numbers and see which one's already balanced, which one I have to actually pay attention to. I see that Ca and Al are already balanced, they're 1 each. Cl on the left is 3, Cl on the right is 2. So those are the numbers I'm going to try to balance out. So what do 2 and 3 both go into evenly? And they go into 6. So I'm going to take the Cl's on the left, and I'm going to apply all this stuff over here by 2. That'll give me my 2 times 3 is 6 Cl's right here, but it's also going to change how many Als I have. So now instead of being 1 Al, I have 2 Als. Let's see how that affects the stuff on the right. Ca is still balanced on each side, but we were trying to get to 6 chlorines to make that numbers even, so I'm going to write a 3 right here. That'll give me my 6 chlorines. 3 times 2 is 6, but we now also change the number of Cas. So 3 times the unwritten 1 will give me 3 Cas on the right. Those are the only things I changed, so let's now recount. Cas are currently unbalanced, 1 on the left, 3 on the right. Al is currently unbalanced, 2 on the left, 1 on the right. My chlorines are balanced, though, with 6 on each side. So it doesn't matter which one we do first. The Ca on the left and Al on the right are by themselves. We can just put any number we want there to make it balance out. So to make this Ca on the left, the 1, look like a 3, I'm just going to go ahead and write a 3 right there. And that should give me now 3 Cas on the left to match the 3 Cas on the right. Same thing over here. We've got the Al by itself, so I can write any number I want on that line. And I want to make this 1 look like these 2. So I'm going to write a 2 right there. That's going to give me 2 Als on the right. I can recount now. 3 and 3, the Cas match. 2 Als on the left matches the 2 Als on the right. 6 Cls on the left matches the 6 Cls on the right. Looks pretty good. 3, 2, 3, 2 cannot be reduced. That's my simplest balanced equation, and we're done. I showed you an example like this in class today on the board. This looks weird, right? It's big, it's a long equation, there's lots of stuff going on, it's just a lot more complicated and probably a lot more confusing than a lot of the ones we've seen either on the worksheet or that we went over together on the board. Doesn't matter, do it all the exact same way. The way you're going to do this, though, is as soon as you see those parentheses, you know, right in the side of the parentheses, that's a polyatomic ion. That's the only reason you use parentheses. It's to show that that's an ion that stays together. And I see a PO4 over here. Well, look, I also see a PO4 all the way at the end over here. It's staying as one piece. It's just moving around. It's changing partners. Over here, the PO4 is paired with Ca. Over here, the PO4 is paired with Al. In the same way, I see an SO4 in parentheses on the left, and I see an SO4 over here, not in parentheses, on the right. On the left, the SO4 is paired with Al. On the right, it's paired with the Ca that used to be paired with PO4. They all just changed their partners. They kind of swapped and flip-flopped around. Once you see those parentheses, you know you're just going to treat those elements as one piece. The ion is going to be treated as one big thing. Don't try to break up and balance the P's and the O's separately. Just treat it as one piece. So I'm going to write right here Ca, and then I'm going to count my PO4s because I'm treating it as if it was one element. And then I'm going to balance out my ALs, and then I'm going to balance out my SO4s. And I'm also treating that polyatomic as if it was one element. On the right, the same exact thing. Ca, PO4, Al, and SO4. I'm going to count over here. I've got 3 CAs on the left. And this little 2 right here means that I have 2 of this entire big thing with the PO4. So I have 2 PO4s on the left. Right here, the little 2 tells me I have 2 ALs on the left. And right here, the little 3 again tells me I have 3 of everything in those parentheses. So I have 3 of this whole big polyatomic that we call SO4. 3 of that. On the right side of the arrow, there's no number next to Ca, so I only have 1 Ca. There's no number next to, again, it's SO4 as a whole big unit. The 4 only refers to the oxygen in the molecule. That's not telling us anything about the whole piece. So it's just 1 of this SO4. There's no number next to Al, so there's also 1 of the Al. And just like over here with the SO4, there's no number next to PO4, so there's also 1 of PO4. Now I can look at these and try to compare. I see that the CAs are unbalanced, the PO4s are unbalanced, the ALs are unbalanced, and the SO4s are unbalanced. So again, it does not matter where I'm going to start, but I just always do it. When I see this polyatomic, I just really want to get that out of the way and start there. I think that makes it a lot easier. If you go that way, I feel like it always kind of steers you in the right direction, says, now you need to do this. So I'm going to go and look at this because it's the 2. I see there's 2 PO4s on the left, only 1 PO4 on the right. I want to balance those. So I'm going to multiply this molecule to PO4 and over here by 2 to make those numbers balance. Now I know I've got 2 PO4s on the right to match my 2 PO4s on the left. That's taken care of. But when I put the 2 there, I also multiplied the aluminums by 2. So now I have not 1, but 2 aluminums on the right. That's okay though, because if we look over here, we also have 2 aluminums on the left. So right there, we took care of 2 birds with 1 stone. We got our PO4s balanced. We got our aluminums balanced. Now I can worry about the other ones. I'm going to go to the other parentheses, just like I did with the first thing. I see the 3 right here. That means we have 3 of the SO4. We had them on the left. There's only 1 SO4 on the right. I want to make this one look like these 3. So I'm going to multiply this molecule right here by 3. That's going to give me 3 of the SO4. It also is going to multiply the calcium. So it's going to give me 3 of the calciums. Oh, wrong line. 3 of the calciums. There we go. I'm going to recount now. And I've got 3 calciums on the left, 3 calciums on the right. I've got 2 PO4s on the left, 2 PO4s on the right. I see 2 aluminums on the left, 2 aluminums on the right, 3 SO4s on the left, 3 SO4s on the right. Everything's balanced. I'm going to finish it off just by writing a 1 over here and a 1 over here. So anyone looking at this knows I didn't just forget to put something there. Then I'm going to come back to it later. Never write a 0, remember. Done, balanced, 1, 1, 3, 2, can't be reduced anymore. That is, again, my simplest balanced chemical equation. Here we have a question from the June 17 Regents. So this is a question that the current seniors would have seen on their Regents if they took it as sophomores. This is a question I'm not really particularly fond of, but I want to show you as an example of just what might be a little bit challenging. I don't really like this one because usually it doesn't matter where you start, it's all going to end up the same anyway. If you started trying to balance the ends, starting with the H's, the O's, it's not going to make a difference. But this question really seems to. I actually started recording this slide before. I started with the ends first and then worked around, and I got to a point where suddenly I said, oh, right, okay, this isn't going to work out too well. I think it's much easier to start with the O's. Sometimes it's just the way it works out. You kind of hit roadblocks as you go. So I think it's a good example just to kind of look at and see how you might try to approach these things. So I'm going to write now here my N's, H's, and O's. And just notice the ones we did in class today where I was saying, oh, this is a trickier one, you're not really going to see ones like this. That was mainly because you were seeing things like two different places where the same element was on the same side of the arrow. So maybe it would be like an O2 and O2 or something like that, where you had to kind of balance the same element twice. That doesn't happen here. We only have N, H, and O in separate place on the left, and H and O in separate place on the right. It really should be an easy one. It's just what approach you take to actually solving this can kind of make a difference, and it makes it a little bit easier to do it one way rather than the other. So I had an easier time doing it the O's first. I'm going to do that right now. So I'm going to start out. I have my one N on the left, I have three H's on the left, and I have two O's on the left. On the right side now I have two N's, I see two H's, and I see one oxygen. Like I said, I'm going to start with the oxygens because I think that makes it a little bit easier to do from that approach. If you get to a point where you're looking at the numbers saying, oh, it's just a little bit tougher, it doesn't quite make sense, you can always start over and just see, well, maybe it does make it easier if you start with one element as opposed to another one. And that's exactly what I found here. When I start with the N's, I could still solve the problem. It just, I had to do a little bit trickier, and I wasn't really comfortable showing you that how to do it that way. So I didn't want to do it. Let's try it this way. I have one oxygen on the right, and I have two oxygens on the left. I'm going to put a 2 right here to multiply this whole molecule over here by 2. That gives me the two oxygens to balance out. It also, though, changes my hydrogen number, and it gives me now 2 times 2 is 4 hydrogens. So I've now balanced my oxygens, but I messed up the balance. With the H's, I have 4 on one side and 3 on the other, and my nitrogens are still unbalanced. I have 2 on the right and 1 on the left. So let's go and let's do the H's because that makes sense, right? I already messed up the H's. Let's go and try that over here. So what do 4 and 3 go into? They don't go into each other. We can't just use one to balance the other. But I know that 4 times 3 is going to be 12. So I can try to make both these things look like 12. So I'm going to take the 3 H's on the left, that's in the NH3 molecule over here, and I'm going to try to make those 3 H's look like 12 H's. So I'm going to write a 4 right here, multiply the whole molecule by 4. That's now going to give me 4 times 1 is 4 M's, and like I just said, 4 times 3 is going to be those 12 H's. On the right, we were trying to make everything look like 12 for the H's, so I had 4 H's to begin with, but the 4 was really only because it was 2 times 2 right here. So if I want to, I could really just kind of multiply this whole thing by 6, or we could just say, well, I had the 2 to begin with right here, next to the H, I can multiply that by 6. I'm just going to say I want it to be 12, so I'm going to put a 6 right there. You don't have to keep that number you wrote originally. You can erase these things as you want. You can change the coefficients as much as you need to. So you don't have to keep like piling up numbers like this times 2, and then this times 2, and this times 3. You can just go ahead and erase whatever number you wrote and write a new number entirely. So I'm just going to make that a 6. If I know I'm trying to get 12, I can now do 6 times the 2, and that gives me the 12 H's to balance out. I'm just going to erase this whole thing actually over here to give me the 12 H's on the right that matches the 12 H's on the left. All right, so let's look at this and count. We have 12 H's on each side. We have 2 oxygens on each side. It's just our nitrogens are now a little unbalanced. We have 4 nitrogens on the left and only 2 nitrogens on the right. So to make these 2 nitrogens look like the 4 over here, I'm going to multiply everything by 2. I'm going to write 2 right there. And that should now give me 2 times 2 is 4 nitrogens on the right, just like the 4 nitrogens on the left. Everything looks pretty good. I have now 4 nitrogens over here, 4 nitrogens over here. 3 times 4 is 12 hydrogens over there. 6 times 2 is 12 hydrogens over there. But the oxygen's unbalanced because when I multiplied everything by 6, I changed this. This now becomes a 6 oxygens on the right. I still only have 2 oxygens on the left. So I need to make these 2 look like these 6. And to do that, I can just write a 3 right there. 3 times 2 is 6 oxygens on the left. To balance the 6 times 1 is 6 oxygens on the right. Now we're balanced. 4, 3, 2, and 6 cannot be reduced. So 4 NH3s plus 3 oxygens, O2, yields 2 of the N2s plus 6 waters. That's my balanced chemical equation. It took a couple of weird steps. It gets a little complicated. You got to keep kind of checking yourself over and over again. This would be a higher level question. This And this was a tougher reading question. Like I said, I don't really like this question. If you did it with the ends, it's going to be a little bit trickier. And I'll show you in a different question how you could actually approach it like that, where you do some kind of trickery to make the math work. Last one we'll do, and this is one of those ones that we've seen where it gets a little tricky because, like on the right side here, you have oxygen in two different places. You may have different elements kind of showing up in different mobile places. It gets tough to look at. So I'll show you a trick that I use that seems like it helps. There's no real process to go. You just kind of have to get used to it and see where it fits in. I'm going to start out the same way, and I'm going to count my FEs, my S's, and my O's on the left. I'm going to count my FEs, my S's, and my O's on the right. So on the left, I've got 1 iron, 1 sulfur, 2 oxygens. On the right, I have 2 irons, 1 sulfur. But now we look at oxygen here and oxygen here. So we have to count everything all together. There's 3 oxygens in this molecule and another 2 oxygens in this molecule. So it's 5 oxygens overall. And this is, again, where it gets tricky. You have to remember that they're in multiple different places. So we have to keep checking both those places. Looking at this, I see that sulfur is currently balanced, so we don't have to worry about that. Iron is unbalanced. There's 1 iron on the left, 2 irons on the right. And oxygen is also unbalanced. 2 oxygens on the left, 5 oxygens on the right. But again, those oxygens are in 2 different locations. I'm not going to worry about them right now. I'm going to hope that it'll kind of sort itself out. Let me go over the iron and get that out of the way because that's only 1 on each side. So I can see my 1 oxygen on the left, 2 oxygens on the 1 iron on the left, 2 irons on the right. I'm going to start there and let me try to do that. So I want to make this 1 iron over here. It look like 2 irons over here. So I'm going to write a 2 right here. Multiply that iron by 2 to get it to be 2 irons on the left. Then that balances out the 2 irons I have on the right already. But when I put that 2 there on the left, I also multiplied the sulfur by 2. So I'm going to get rid of this 2 and recognize that I have 2 sulfurs now. Now if I look and compare, my irons are balanced, my sulfur is unbalanced, my oxygen is unbalanced. I'm going to keep that oxygen for last again because it's the one that shows up multiple places. So I'm going to try to balance the sulfur first. Sulfur had 2 on the left, 1 on the right currently. So I now want to try to get this 1 sulfur over here to look like these 2 sulfurs over on the left. So I'm going to make a 2 right here. That now gives me 2 sulfurs on the right to go along with the 2 sulfurs on the left. So far so good. My iron is now balanced. My sulfur is now balanced. I'm still left, unfortunately, with these oxygens. And that's, again, the weird one because they're in 2 different places. I've got 3 and 2. And because this is an odd number, you can't just put a number here because it's never going to totally add up. You're going to have 5 total. Like this is a negative number. This is a positive, not negative, an odd number. This is an even number. It's just going to make it a lot difficult to look at. So what I'm going to do is I'm going to see that I have now recounting 3 oxygens here. I now have 2 times 2 is 4 oxygens over here. So that's going to be 7 total oxygens on the right side of the arrow. I have to try to get these 2 and these 7 to look alike somehow. I have to try to balance those. So I want to say now, what can I multiply these 2 oxygens here by to make them look like the 7? And obviously there's no whole number we can do that. There's no solid number without a decimal we can use to make that happen. And that's okay, because that's the trick I'm going to show you. If I multiply 2 times 3.5, I can make it work. We want whole numbers, we want solid numbers without decimals as our coefficients, but at least in this little interim step, we can do this. We can multiply this whole thing by 3.5. And that would make it work, because we do 3.5 times 2. That would give us 7. That works fine. But we don't want to leave it as a 3.5. So how are we going to get around that? Well, once we have that 3.5 here, we can just figure out a way to make this 3.5 look like a whole number. And the easy way to do that is just to double it. Anytime you get to this step, and you're saying, oh, well, it's just, there's no whole number that makes it work. If you can get a number that's something 0.5, that's fine. Write that number there to make it balance, and then just multiply it by 2. You can always double a number to get it to be a whole number. So if I now just double everything, it's like having a recipe. If you know you need these number of ingredients to make 1 batch of cookies, you would just double everything to make 2 batches of cookies. You could cut everything in half to make a half batch of cookies. So I can just double this number here, and I'm going to double 3.5 and make that 7. But now I got to do the same thing everywhere else. I'm going to double this number on the left and make that 2 look like a 4. I'm going to double the 2 over here and write a 4 right there. And this was going to be a 1. I'm going to double that and make that a 2. So I'm going to just erase my numbers at the bottom now and recount and see if it adds up. I have now 4 times 1 is 4 irons on the left. 2 times the 2 is 4 irons on the right. 4 times the 1 is 4 sulfurs on the left. 4 right here times the 1 is 4 sulfurs on the right. On the left side, I have now my 7 times the 2 is 14 oxygens. And again on the right, remember we have oxygens multiple places. So the 2 times the 3 is 6 oxygens in the 1 molecule. And now also the 4 times 2 is 8 oxygens in the other molecule. Just add those up. 6 in one molecule, 8 in the other. Well, it gives us 14 oxygens, which balances out with the 14 oxygens over there. So it works. If you get to the point where math doesn't seem like it makes sense because you can't get to be a whole number, that's fine. Write it as something 0.5, and then just make sure you double everything. Then it's going to work. We can look at it 4, 7, 2, and 4 cannot be reduced. This is our lowest number reduced balanced equation. Weird trick, but if you play with it, you can get the hang of it.